This webcast talks about Newton's second law, and we're first going to look at how to apply Newton's second law in situations where all of the forces are parallel to a single axis. So we just finished the elevator lab, and so these first few situations involve an elevator. So at first we're looking at an elevator that's going up, moving up with a constant velocity. And so of course we've learned from the balanced force model that tells us that the net force is going to be zero in this situation. If we look at the forces on this passenger, there are only a couple. Of course there's a gravitational force pulling the man down toward the center of the earth, and let's see, he has a mass of 85 kilograms, and so his weight, or the force of gravity on him, is 833 newtons. And then the floor of the elevator is supporting his weight, so there's a normal force being exerted on the man by the floor of the elevator. Okay, those are our only two forces. And so if we wanted to calculate the force that the floor is exerting on the passenger, well, we know that the net force in this situation is zero because of the constant velocity. And then if we were to look at the force diagram and add up these forces, that would tell us that the net force is the normal force minus the force of gravity. Therefore, the normal force equals the force of gravity, which equals 833 newtons, when the elevator is moving at a constant velocity. Those two things are equal. Okay, now same man, same elevator, but now it's telling us, oh, he's accelerating upward at 2 meters per second squared. Well, one thing I know for sure is that the net force is not going to be zero, and in fact, the net force is going to be pointing up, right? Because acceleration and net force always point in the same direction. So it is the same force diagram with the gravitational force pulling the man down and the normal force pulling the man up. In this case, they are not equal, and so it says write an equation for the vertical forces. Well, I know that the sum of these forces is the normal force minus the force of gravity. That's not very helpful yet, because there are three things in this equation. The only thing I know is the gravitational force. It's that same 85 kilogram man who has a weight of 833 newtons. So I know Fg, but I do not know either the normal force or the net force. But we learned another equation that involves net force. That is that acceleration is the net force divided by the mass. And so I could shift this around to solve for net force. That would tell me net force equals the mass times the acceleration. This is a way of expressing Newton's second law. And you know, we derived this equation in the lab that we did recently. So I have another way of expressing net force, and it is the mass times the acceleration. I happen to know both of those things. Okay, because I know that this man's mass is 85 kilograms. It tells me that the elevator is accelerating him upward at 2 meters per second squared. So the net force must be 170 newtons. Now that I know net force, I can come over here and solve for the normal force. Well, actually, I guess I'll do it down here. The normal force is going to be the gravitational force plus that net force. So that's going to be 833 plus the 170, which is 1003 newtons. So this problem illustrates the strategy that we're going to use in solving most of the problems that involve Newton's second law. And I'm going to type it since it involves some things I can type better than I can write. So the strategy is that we're going to express net force in two manners, okay, two different ways. First, we're going to use Newton's second law, and that tells us that the net force equals mass times acceleration. Then the other way is we're going to find, well, what happened here? We're going to find the vector sum of all of the forces from the force diagram in the direction of motion. So in this case, that net vector sum was the normal force minus the gravitational force. The specific forces that will be involved may depend on the situation, but if you look at the force diagram, since this elevator is moving in the vertical direction, I would want to take the sum of all of the forces in the vertical direction. Okay, so this is going to be our strategy going forward for these problems, is finding net force in two ways. Okay, let's look at another example. So now we're talking about the elevator as it gets close to the top floor, and now it's accelerating downward at 3 meters per second squared. What they mean is that the acceleration is negative, so it's a negative 3 meters per second squared acceleration. Now our force diagram has not changed. This is still a man riding in the elevator, and so there's a gravitational force pulling him down, and there's a normal force supporting him. Okay, but since the acceleration is in the negative direction, I know the net force is also in the negative direction. And if we wrote an equation for the vertical forces, well, I'm going to use the strategy that we just talked about, and I'm going to express net force in two different ways. So first of all, I'm going to look at this force diagram, and I see that the net force is the normal force minus the force of gravity. But then I'm also going to use Newton's second law, which says that net force is the mass times the acceleration. And so if I want to find the normal force here, that's going to be the force of gravity plus the mass times the acceleration. Remember, the gravitational force has not changed. It's the same man. Okay, so that's 833. His mass is 85. The acceleration is -3 in this situation, and so the net force when he's moving down and speeding up, or I'm sorry, when he's moving upward but slowing down, is 833 plus 85 times -3, and we get 578 newtons. Okay. If the elevator broke, or if the cable broke as the elevator is descending, at that point, there is no more normal force, right? There is just a force of gravity still on this man. The elevator is no longer able to provide a normal force because there's no longer a cable holding the elevator in place. So, the net force would be the force of gravity, which would be -833 newtons, right, since it points down, and the acceleration would be negative 9.8 because he would be in free fall. Okay. Let's look at number 5 about a skydiver jumping out of an airplane. So here, and first it says we're looking immediately after jumping. So immediately after jumping, the velocity is not very fast yet. And so therefore, air resistance is negligible. So if we can ignore air resistance, then the only force on this skydiver is the force of gravity. They're in free fall, in other words. And it asks about the acceleration. Well, the acceleration, or let's see. Yeah, the acceleration is the net force over the mass. Well, the net force is minus the force of gravity. And that force of gravity would be 70 kilograms times 9.8. And of course this force is pointing down, so I'm going to put a negative sign. The mass is 70 kilograms. So look at this. It's going to be negative 9.8 meters per second squared. So in free fall, we've learned before, acceleration is the acceleration due to gravity, which is negative 9.8. But after the skydiver is falling for a while, he gets to be going very fast. And as his speed increases, the drag force due to air resistance also increases. So at some point, he's reached a speed of 100 miles per hour. So now, drag due to air resistance has become significant enough that we need to take it into account. And they're telling us that it is 300 newtons. And of course we know the force of gravity on this skydiver is 70 times 9.8, which is, well, 686 newtons. Okay, so we want to find the acceleration in this situation. I'm going to use two methods to define net force. First of all, it is the drag force minus the force of gravity, right? I'm looking at the force diagram and taking the vector sum of the forces. But the second way that I can express net force is by the mass times acceleration. In this case, I'm looking for acceleration. So the acceleration is going to be the drag force minus the force of gravity divided by the mass, which is negative 386 divided by 70. And so that's going to be negative 5.514 meters per second squared.